Hello everyone, happy to see you here on my channel. Hi, I'm Mathematics, and today we have a really interesting question, 1 to the x equal to minus 4. On the first side, this is a very simple question. We don't have like a complicated expression with sine, cosine, with square roots right here. We have regular expression, we have 1 minus 4. But when we look closely, 1 to the x equal to 1 all the time in terms of school knowledge. Yeah, we have all the time 1 because 1 to the power 100 equal to 1, 1 to the power 1000 equal to 1, and we have right here minus 4, so it's not like a huge complicated expression. But when we look closely, 1 on the left side and minus 4 on the right side, constant and constant, positive, negative, so how is it possible? In terms of maths, we can solve this challenge like that. So when we study at school, we can easily solve this challenge like that. We can easily apply natural log on both sides, so we have natural log of 1 to the power x equal to natural log of minus 4. And right now, x will come down right here because according to the main log property, as a result, we will have like x times natural log 1 equal to natural log minus 4. And right now, we can easily divide both sides by this natural log 1, yeah? And then we will have our x on the left side. So x equal to natural log of minus 4 divided by natural log 1. And in terms of school knowledge, this is enough, because right now we can easily say that natural log 1 equal to 0, and natural log 4 does not exist. So in terms of real number roots, natural log of a negative, we learn at school that natural log need to be positive, so every time need to be positive value. Right here we have negative, so we can't evaluate, we can simplify this expression in our numerator. But basically we can't divide it by 0. So in terms of school knowledge, this is enough for you, because you don't know what will happen when we divide it by 0. We don't know what will happen when natural log is negative. But in terms of real numbers, this is enough. In terms of complex numbers, we can find our roots. So let's look at these notes. Let's look at this solution. So right now, let's try to solve it. According to this step, we can easily say that right here we have no real roots, and this is the proof, because right here we divided by 0, and this is like we can't evaluate this expression in our numerator, so no real roots. But when we don't have like real roots, we can easily find our complex roots. So in this video I'm going to show you my approach. How can we find our complex roots? How can we find our roots to this question? So first of all, I want to start with this complex unit. So how can we create complex unit? I suggest you to look at this Euler's identity. This identity looks like that: e to the power I times theta equal to cosine theta, yeah, plus I times sine theta. And I want to use this identity in a further solution. But first of all, let's check this identity. Let's prove this identity real quick. Maybe someone don't know how this identity works. For example, when theta equal to, let's go with theta equal to 0, it's easier for us to plug in, instead of theta, let's plug in 0. As a result, what we will have? We will have e to the power I times 0 equal to cosine 0 plus I sine 0. Okay, cosine 0 equal to 1 and sine 0 equal to 0. And right here we have e to the power 0, which is equal to 1. So as a result, we have 1 equal to 1. So this is a great identity. But I don't need exactly the same identity as right here. I want to make a substitution. This substitution will help us a lot. So take a look closely what substitution I will use. This substitution looks like that. So theta equal to 2k pi. This is our substitution, and k is integer, so k is integer number, and k equal to 1, 2, 3, 4, as you can see, all integer values. So I'm going to plug in, instead of theta, I'm going to plug in this substitution. So how does our Euler's identity looks like? Our identity looks like that: e to the power I times 2k pi. Okay, instead of theta, we're going to plug in this 2k pi equal to cosine 2k pi and plus I times sine 2k pi. Okay, so instead of theta, we're going to plug in this 2k pi. And here is right now the key moment, because I'm going to look what will happen when k equal to 1, 2, 3, and 4. This is really interesting moment right now, okay? So first of all, let's start with k equal to 1, okay? Let's start with the beginning. So for k equal to 1, when k equal to 1, what we'll have as a result? E to the power I times 2 pi, equal to cosine 2 pi, cosine 2 pi plus I sine 2 pi. And right now, cosine 2 pi, we can easily know it from school, and sine 2 pi equal to right here 0, right here 1. So this expression on the left side equal to 1 plus 0 equal to 1. Really great. Right now, let's see what will happen when k equal to 2. Let's see the difference. Let's try to find the pattern between these lines. So for k equal to 2. So when k equal to 2, what we'll have as a result? We will have e to the power I times 4 pi, yeah, equal to cosine 4 pi plus I sine 4 pi. Really great. And right now, cosine 4 pi, this is like a period. So 2 pi, 4 pi, 6 pi. So right here we have the same one. And on the right side right here, we have sine 4 pi equal to 0. So as a result, we have the same one. Really great. Right now, let's see what will happen when k equal to 3. Okay, so for k equal to 3. When k equal to 3, what we'll have as a result? E to the power I times 2 pi times 3, we have 6 pi, equal to cosine 6 pi plus I sine 6 pi. Okay, really great. Equal to the same 0, the same 1, because right here cosine 6 pi equal to 1 and sine 6 pi equal to 0. So we have the same one. And right now, finally, let's look, for example, when k equal to 4. Let's look at it. This is like a final substitution. When k equal to 4, what will happen when k equal to 4? As a result, we have e to the power I times 8 pi and equal to, right here we have equal to cosine 8 pi plus I sine 8 pi. Okay, right now the same thing, sine 8 pi equal to 0 and cosine 8 pi equal to 1. As a result, 1 plus 0 equal to 1. As you can see right here, we can easily see this pattern when k equal to 1, 2. So when k is integer, on the right side all the time we have 1, 1, 1, 1, 1, and it doesn't matter this expression on the left side. As a result, we have all the time 1. When k is integer, 1, 2, 3, and 4. But for those who are interested, for example, who don't trust me when, for example, k, let's look at this final step. So for k, let's go with 500, something like that, 500. Well, what will happen right like that? E to the power I times 500 times 2, we have 1000 pi equal to cosine 1000 pi plus I sine 1000 pi. And let's see what will happen right here. Cosine 100 pi, this is like the same cosine 2 pi, but we have the period, we jump right here, we jump in this point like 500 times. So as a result, in this case, we have 1 and 2000 pi, 3000 pi, 1 million pi, we have all the time 1. And sine, this is like the same period, we have all the time 0. And 1 plus 0 equal to 1. So I hope you understand my thoughts. I hope you understand my approach. When k is integer, this expression in Euler's identity, this one, is all the time equal to 1, all the time when k is integer. Right now, let's write this thing, let's write this general case right here. Okay, so after these steps, after this finding k equal to 1, 2, and 3, let's write our question. So e to the power I times 2k pi, so e to the power I times 2k pi equal to 1 when k is integer. Okay, k is integer, and k equal to 1, 2, 3, and a lot of these values. So right now, I hope you understand this step. This expression equal to 1 when k is integer. We proved it before a lot of times. And right now, let's go back to our question. What we had in the beginning, we had 1 to the x. Okay, here's our question. 1 to the x equal to minus 4. Here's our question. And right now, let's gonna plug in, instead of this 1, let's gonna plug in this expression when k is integer, this expression equal to 1. So instead of this 1, let's plug in this expression. What we will have as a result? We will have, let's write it right here in the new line. So we have right here e to the power I times 2k pi to the power x equal to minus 4. Okay, so I hope you understand this step. We're gonna plug in this expression instead of this 1. Right now, how can I solve this challenge? How can I solve this equation? First of all, let's apply natural log on both sides. When we apply natural log on both sides, we have right here on the left side, we have right here natural log e to the power I times 2k pi times x. Okay, we can multiply this expression by x because we raised to this power, equal to natural log of minus 4. Really great. Right now, this power will come down right here, okay? Because this is like the main log property. That's why we do this, because we need to bring this expression right here in this place. Okay, so we have I times 2k pi times x times natural log e equal to natural log of minus 4. Really great. Right now, we need to find our x. We don't need all of these expressions, and obviously natural log e equal to 1, so we can easily cancel this. And as a result, we need to remove this expression from left side. How can we do this? We can easily divide both sides by this expression. So as a result, we have in our numerator, we have I times 2k pi x, and we divide this expression by I times 2k pi, and equal to natural log minus 4 divided by I times 2k pi, so the same expression, I 2k pi. Right now, from here we can cancel this. As a result, we have only our x. So our x equal to natural log minus 4 all over I 2k pi. But k is z and k is 1 to the set of 1, 2, 3 of the set of integers, yeah? So I hope you understand this step. Right now, let's simplify this a little bit. Let's multiply numerator and denominator by I. As a result, when we multiply our denominator by I, as a result, we have I squared. But in terms of complex number, we know that I squared equal to minus 1, yeah? In terms of complex numbers, so our final sign will be negative. So we have minus I natural log of minus 4 all over 2k pi, and k from here, k is not equal to 0, k is integer, and k, for example, is 1, 2, 3, and a lot of this value. So this is our first step. We find our x equal to minus I natural log minus 4 all over 2k pi. What about our denominator? 2k pi, everything is great for us. We can simplify this more. This is I, this is complex unit, and that's why, of course, we find our complex solution. But this natural log minus 4, in terms of complex number, we can easily rewrite it. And right now, I'm going to show you how can we rewrite this natural log of minus 4, and then we're going to plug in this expression. I'm going to show you this expression here in just 1 minute, and then we're going to plug in this expression instead of this natural log minus 4. So let's do this right now, because natural log of a negative value, we can't solve this, we can't find this value in terms of real numbers, but instead of complex numbers, we can easily do this. So right now, let's evaluate, let's rewrite a natural log of minus 4. So let's do this right now. Okay, so from the previous step, we know our equation 1 to the x equal to minus 4. We know our x equal to minus I natural log minus 4 all over 2k pi. And right now, as I told before, we're gonna rewrite this natural log of minus 4 in terms of complex number, because in terms of real numbers, we can't simplify this natural log of minus 4 because this is like not possible. Natural log function cannot be negative in this place. So right now, natural log of minus 4, let's rewrite it a little bit. So we have natural log of minus 4. How can we rewrite it? We already know that this is not like a real number value, because natural log of a negative value right here is not possible. So right now, let's write this minus 4 as minus 1 times 4. So we have natural log of minus 1 times 4. And right now, I hope you understand, I hope you all remember from school that if you have natural log, or doesn't matter, log basically, yeah, a log of a product, we can easily write it as a sum of two logs. Okay, so this is equal to, we can write here natural log of minus 1 plus natural log of 4. Really great. And right now, natural log of minus 1, we can rewrite this expression in terms of Euler's identity. Okay, natural log of minus 1. Let's rewrite this expression first of all, and we have natural log of 4. So let's leave it this expression like that. But natural log of minus 1 can be written as according to the Euler's identity. So this is equal to natural log of, right here we have e to the power I times pi plus 2 pi. Let's go with m, for example, because we need the period right here all the time, and m is integer right here, okay? So, and we close this, and plus natural log 4. And of course, m is integer, okay? Don't forget about this. Right now, natural log of e equal to 1, and as a result, this power, this expression will come down before this become this natural log. As a result, we have I times pi plus 2 pi times m, okay, and plus natural log 4. Really great. Right now, let's factor from here pi. We can easily do this, because right here we will have time like I times pi, or let's write this parenthesis at first. So we have 2m plus 1 times I times pi, and plus natural log 4. So really great. But all the time we have equal sign, and this is our natural log of minus 4. So instead of natural log minus 4 in the beginning, let's plug in this expression. Okay, let's do this right now. So what do we have as a result? We have x equal to, we have minus I and times natural log of minus 4. Okay, so minus I and times this natural log of minus 4, which is equal to 2m plus 1 times I times pi, and plus natural log 4. Really great. And we close parentheses and we divide all of the thing, don't forget about this, by 2k pi. By 2k pi. Really great. Right now, let's simplify this a little bit. Let's multiply this I by this parentheses. So what do we have as a result? We will have as a result that x equal to minus, and we multiply this I by these whole parentheses. So let's do this right now. What do we have as a result? We will have inside parentheses, we have I squared times pi and times 2m plus 1, okay, and plus I natural log 4. And all over 2k pi. All over 2k pi. Really great. I square equal to minus 1. I wrote it before. I square equal to minus 1. This is our complex unit. So as a result, what we will have? We will have x equal to minus, and inside parentheses we have minus pi times 2m plus 1 and plus I natural log 4, and all over 2k pi. All over 2k pi. But right here we don't need this line. Yeah, x equal to, okay, something like that. Right now we can easily open our parentheses, something like that. We can easily do this. Right here we have minus, I guess. Yeah, we have minus. And as a result of a final answer to this challenge, x equal to minus gives us plus. So we have 2m plus 1 times pi minus I natural log 4, and all over 2k pi. And this looks like our answer. We have 2m plus 1. We know that m is integer. We have pi, we have I, we have a complex units right here. So everything is great, I guess. So let's write our final answer to this question. So our final answer, x equal to 2m plus 1. So let's split this part with this final answer. So we have right here 2m plus 1 times pi minus I natural log 4. We can rewrite it as 2 natural log 2, but it doesn't matter right here. Okay, and we divide all of the thing by 2k pi, but k is not equal to 0, because in denominator k is integer. For example, k equal to 1, 2, we proved it before, and m is also integer. Okay, m is integer. So this is a solution when all of this rule works. Okay, this is a solution when all of these roots works together. But we don't know what will happen, for example, when k is like a rational number, k is, for example, a fraction, k is a decimal value. We don't know what will happen there, because this solution is about this part when k is not equal to 0, k is integer, k is equal to 1 to 3, and a lot of these integer values, and m is integer. But we don't know what will happen when k is equal to 2.5, when m is equal to like a sine like 60 degrees. We don't know what will happen there. But when all of these rules work together, our answer is this one. So when 1 to the x equal to minus 4, when k is not equal to 0, k is z, k is equal to 1 to 3, and a lot of these values, and m is integer, a root to this question, x equal to this one, of course, in terms of complex numbers. As I told before, when you study, for example, in school, your answer is the next one, x equal to natural log of minus 4 all over natural log 1, and you write the next thing, natural log equal to 0 right here, and right here does not exist. The numerator does not exist. So when you study at school, this is enough for you. You don't know about complex number. Moreover, you don't know about complex. You don't know about Euler's identity. Yeah. So maybe if you study at school, this is your answer only in a few or in a 3 or 4 lines. But maybe someone interested in this question, maybe someone study in a university, maybe there are a lot of teachers. I wanted to show this approach. This is not like a general approach. We don't know what will happen when k is like 10.5, when k is -1. We don't know what will happen there. We don't know what will happen when we have a negative value. As you can see, we have some part of positive part, but when k is negative, when k is -1.5, we don't know what will happen there. So this root is not working in negative plane, is not working in all real numbers. This root is only great when k is integer, when m is integer. So this is like a general root according to these lines. Okay, this is a general root. But what will happen in infinity? What will happen in negative plane? What will happen when km is negative? We don't know about it. And of course, this is our approach. This is our explanation to this challenge. You can also write your thoughts down into the comment section. Write your notes about it. Maybe you have your interesting approach. Maybe you solve this challenge not according to Euler's identity. It will be really great to see your solution. Maybe there are a lot of teachers who watch my channel and want to share your response into the comment section. It will be really interesting to read about it, and also write your thoughts about this challenge. I really appreciate it if you enjoy this video, if you learn something new, if you like a great thing in terms of math in this video. I really appreciate it. So thank you for your time, thank you for your support, thank you for your kind comment, thank you for your response. And if this video is helpful in any way, don't forget to like and subscribe. That definitely helped me out now for this particular video, and I hope you enjoyed. I hope you learned something new. So thank you for your time, have a great day. I wish you all the best in your mathematical adventures. See you in the next videos.